Okay, let's look at section 7.1, radicals and radical functions. And the easiest and the first radical that we're going to look at is the familiar square root. So notice this says a. Recall a square root of a number c is another number b such that b squared is equal to c. And a was carefully chosen because that's called an indefinite article rather than the, which is a definite article. So let's find a square root of 25. Well, by the definition, a square root of 25 is another number, b, such that b squared is equal to 25. And half of you are out there, I'm hoping, saying, oh, well, let b equal 5. Then b squared is equal to 5 times 5, which is equal to 25. So clearly b equals 5 satisfies the definition of a square root. But also, let's note something else. If b is equal to minus 5, then b squared is equal to minus 5 squared, which is minus 5 times minus 5, which is also 25. So it turns out the following is true. Every positive real number has two distinct square roots. Since if b squared is equal to c, then minus b squared is also equal to c. So we're going to denote either b or minus b is positive. So the positive value of b will be noted as the square root of c. So let's stop right here. I may be going a little bit fast. By what I'm saying right here, I just said by the definition of a square root that if b squared is equal to c, then b is the square root of c. Since minus b squared is equal to c, then minus b is a square root of c. So either b or minus b is positive. So the positive value of b is denoted by this. So in other words, the square root of c always refers to the positive root. And to denote the negative root, we just put a negative sign there. So I have all of this listed right here, so let's just read it. I wanted to give you some examples. So every real number has two square roots. Every real positive number has two square roots. I'll have to add that in there. The non-negative number b, such that b squared is equal to c, is called the principal square root of c and is denoted by this notation. So this number right here is a real number that is positive, such that that real number squared is equal to c. The negative number b, such that minus b squared is equal to c, is called the negative square root of c and is denoted by minus the square root of c. So I'm going to fix a few little typos in this box because the only numbers that have two square roots are positive real numbers. So I'm going to add that in the box. I know you don't care about it, but I do. So let's actually look at exercise 1. (1A). So I'm looking for the positive square root of 36. So when you see this sign, it doesn't mean a square root. It means the positive square root. So I'm looking for a positive number b, so b greater than 0, such that b squared is equal to 36. So let's try 6. So 6 is greater than 0, and b squared is equal to 6 times 6, which is equal to 36. So the positive square root of 36 is equal to 6. So I did all of this because really, you say, why are you doing all of that? We know that the answer is 6, because I want to show you everything in math boils down to the definition. And for the answer to be 6, it has to satisfy the case that b is greater than 0 and b squared is equal to the number under the radical. So let's do 1b. And let's find the square root of 0. Well, this is by definition equal to 0. 0 is not positive, it's 0. It's the dividing line between all of them, and its square root by definition is 0, and there's only one of them. That's the only real number that has a square root such that the positive and negative root are the same, and that's 0. So let's look at the square root of 4 over 49. So again, we're looking for b greater than 0, such that b squared is equal to 4 over 49. Well, let's just try b equals 2/7. Well, 2/7 is clearly greater than 0, and b squared is equal to 2/7 times 2/7, which is equal to 4 over 49. So the answer here is 2/7. And my final example, so literally, I'm using the definition of the positive square root of a number to answer these questions. So 1D, we're asking for the negative square root of 81. But really all we have to do is find these two are the same. So I find the positive square root of 81 and then I negate it. So I'm looking for b greater than 0 such that b squared is equal to 81. If I let b be equal to 9, 9 is greater than 0, and b squared is equal to 9 times 9, which is 81. So this is equal to negative. So the positive square root of 81 is 9. So the answer is minus 9. That's the answer. Okay. So let's go on. Here is a challenge for you, and you actually should easily be able to figure this out by thinking about it, by using the definition. So is there a real number b such that b is equal to the square root of minus 81? Well, let's suppose yes. And let's see where it leads us. It'll probably lead us to a contradiction. then there exists, by definition, a b greater than 0 such that b squared is equal to minus 81. But any number greater than 0 multiplied it by itself is greater than 0. So it is impossible for such a number to exist. So the answer is no such, here is the rub, real number b exists. Nothing satisfies the definition. Now I say real number here because later on in college algebra, and maybe just a tad bit in this class, I can't remember, we're going to introduce an extension to the real numbers called the complex numbers, where this will have an answer. But just stay tuned, just cross that bridge when we get there. So now let's do the cube roots. Cube roots are really interesting, but they're going to be different than square roots. So the cube root of a number c, and that is denoted this way immediately, is another number b, and I'm not saying b greater than or equal to 0, such that b cubed is equal to c. So let's look at some examples. Let's find the cube root of 64. Well, I need to find a number b such that, st always means such that, b cubed is equal to c. Well, let's try b is equal to 4. Then 4 cubed is equal to 4 times 4, which is 16, times 4, which is equal to 64. Well, that's cool. So b is equal to 4 is one answer. Well, what about b is equal to minus 4? Well, let's try it. Let b equal minus 4. Then minus 4 cubed is equal to minus 4 times minus 4 times minus 4. Well, minus 4 times minus 4 is 16, but 16 times minus 4 is equal to minus 64. And we're looking for a number that will give us 64. So b equals 4 is the only solution. So this denotes I don't need to have two different roots or branches here. I don't have to have a negative to denote the negative number b such that b cubed is equal to 64. So when we have, and we'll learn when we have an odd index, the answer is unique, and there's not two. So let's find some cube roots. Not too hard. Again, we're going to find these by looking and using literally the definition. So that's how it always starts. Sometimes using the definition when it's so ingrained is rather difficult, but we're going to do it anyway. So I want the cube root of 1. So I'm looking for a b such that b cubed is equal to 1. Well, if I let b equal 1, then b cubed is equal to 1 times 1 times 1, which is equal to 1. So the cubed root of 1 is just equal to 1. Let's do 2b. let's look at the cube root of minus 64. So again, by definition, I'm looking for a b such that b cubed is equal to minus 64. Well, we just found one, didn't we? If we let b equal to minus 4, then b cubed is equal to minus 4 times minus 4 times minus 4. And literally, we just figured out that that was equal to minus 64. So the cube root of minus 64 is equal to minus 4. And in general, the cubed root of an odd number is an odd number, and the cubed root of a negative number is a negative number, and the cubed root of a positive number is a positive number. And that's going to be true in every case when the index, this little number right here, we'll learn, the 3 right there, is called the index. When the index is odd and the number under the radical is negative, then the answer is negative. When the index is odd and the number under the radical is positive, then the answer is positive. Let's get some more room here. Not doing that, but rather doing this. So let's do 2c. So let's find the cubed root of 8 over 125. So again, I'm looking for some number b such that b cubed is equal to 8 over 125. So let's try b is equal to 2/5. Then b cubed is equal to 2/5 cubed by an exponent property. 2 cubed is 8, and 5 cubed is 5 times 5, which is 25, times 5 again is 125. So the answer here is 8 over, the answer here is not 8, but rather it is 2/5. And for D, 2D, we want to find the cube root of minus 27x to the 15th. So now I'm not looking for a number, but a variable term, if you want to call it that, such that b cubed, whatever that number b is equal to minus 27 over x to the 15th. So again, I'm just kind of doing this now. Let's let b equal minus 3x to the 5th. Then b cubed is equal to minus 3x to the 5th cubed, which is equal to minus 3 cubed by our exponent rules times x to the 5th cubed. Well, minus 3 times minus 3 is 9, times minus 3 is minus 27, and x to the 5th cubed is x to the 15th. So the answer to this is minus 27. The answer to this is, I keep wanting to write the wrong thing, is minus 3x to the 5th. Okay, let's go on down. So finding nth roots. So this is, if we want to think about what we've just done, we notice there's a difference when we're talking about the square roots and cube roots. Well, square roots are going to be represented in this particular way by an index of 2. So let's just look at this right here. Recall this is called the nth root of c. N is called the index. C is called the radicand, but I will probably not use that term. I will rather use the term number or expression as fit under the radical. And that kind of gives you a clue that this symbol right here is called the radical. So the square root of a number, it's the only time that we don't write the index. But the index is understood always when we're talking about the square root. This is equal to an index of 2. So let's keep that in mind. So here we have some cases. And you have to digest all of this. So if the index n of the nth root of c is even, so they're talking about right there, if that number right there is even, so we're talking about square roots, fourth roots, eighth roots, sixth roots, 100th roots. If n is even, then the radicand, the number under the radical, must be greater than or equal to 0 in order for the nth root to be a real number. And right now, that's all we got in our game is real numbers. But on the other hand, if the index is odd, for example, n is 3, 5, 7, 11, whatever, the radicand can be any real number, 0, positive, or negative. As before, if b is equal to the nth root of c, then b to the nth is equal to c. If n is even, there will be 2 nth roots, as in the case when we're talking about square roots, the positive and the negative. If n is odd, there is only 1 nth root. So we're going to use all of that information right there. And all you have to do is kind of just remember the case when we're talking about square roots and when we're talking about cube roots. And then just extend, well, square roots is 2, so that means even index. And cube roots is 3, so that means odd index. And then just generalize from that. So let's look at example, give me my pen here, 3a. Let's go to yellow. 3a. We want to find the fourth root of 81. So this by definition, just like the square root of 81, this is going to denote the positive number b greater than 0 such that b to the fourth is equal to 81. And if I wanted to find the negative value, I would denote it this way. So it's pretty easy fix right there. Well, let's go over here and solve the problem we were actually given. So I'm going to say let's let b be equal to 3. Then b is greater than 0. And 3 to the fourth, now watch this little trick, is equal to 3 squared. Squared. That's by a exponent rule, which is equal to 3 squared is 9. and 9 squared is equal to 81. So the answer is 3. Let's look at another one. So 3b. Now I want the fifth root of minus 243. So since my index is odd, there is no, I just want to find some number b, not b greater than 0, such that b to the fifth is equal to minus 243. So I'm looking for some number b such that b to the fifth is equal to minus 243. So b is going to have to be negative. So let's let b equal to minus 3. Then minus 3 to the fifth is going to be equal to minus 3 to the fourth times minus 3 as I add exponents. Well, we just discovered that minus 3 to the fourth is, in this case, 81 because my power. And if I multiply that by minus 3, let's see what we get. 81 times minus 3 is 3. 8 times 3 is 24 plus 3. That's 208 times, did I write that down wrong? 8 times 3 is 24. Oh, I didn't carry anything. Jesus, what am I doing? So it's minus 243. Why was I thinking I'd carry to 3? No idea. It happens. So the answer is, let's not leave this before I write down the answer. The answer is minus 3. So it's going to, later on, I'm going to talk to you. That means because of COVID-19, you're not taking these in a proctored setting. But for those of you, you've got to think forward. For those of you who pass this class and go ahead and take college algebra, your skills have to be sharp. You really, to be, to have any good chance of passing college algebra the first time around, you need to have a solid B in this course, at least a solid B, and an A is preferable. Because in college algebra, we don't slow down. I just assume you know all this, or whoever your teacher is, they're just going to assume you know all of this, and they're not going to go back and review it for you because you just passed the class, and that's supposed to certify you know it. So I'm going to suggest that you learn a list of cubes. I'll look at those later on in just a second, although I may forget. Let's do 3c. We want to find minus the square root of 25. So all we have to do is find the value of b greater than 0. So I'm just finding this value right here, which is the positive square root of 25, such that b squared is equal to 25. And you already know b equals to 5 works. So this is equal to minus 5. So that one was that they sneaked in an easy one for us there. And 3D. So let's do the cube root of 64x cubed. So I need some expression b such that b cubed is equal to 64x cubed. So we just found out that if b is equal to 4x, well, we may not have just found out this about 4x, we found it out about 4, then b cubed is equal to 4x cubed, which is equal to, see how our exponent rules are coming into play here? Times x cubed, and 4 cubed is what we did find out earlier, so that's 64x cubed. So the answer is 4x. And for those of you who are already a little bit more advanced, we will have a rule that says the cube root of 64x cubed is going to be equal to the cubed root of 64 times the cubed root of x cubed. And that'll make it a lot easier, because then you know automatically it's going to be 4 times x. But we've not been given that rule yet. It's coming. I'm hoping it's coming. At some point, at some point it comes. Okay, here is a rule we're going to use again and again and again. And it has two cases. So how do we find the nth root of a number? So this is a theorem about the nth root of c to the nth. In other words, I'm going to be looking at this, the nth root of c to the n. Well, we have two cases. If n is greater than 0 and even, then the nth root of c to the n is equal to the absolute value of c. On the other hand, so this is case 1. I tell it to you right here. Case 2 is if n is positive and also odd, then the nth root of c to the n is just equal to c. So let me give you an example of that very thing. Really, it only comes into play up here when we add the absolute values. And the only time the absolute values comes into play is when the thing raised to the nth power has a value that is unknown. Because I already know that the square root of 25 is equal to the square root of 5 squared, and that's going to give me 5. But it's also, if you want to think about it, it's equal to the square root of minus 5 squared, in which case it's the absolute value of minus 5. The end result is still 5 in both cases. So in particular, this is when you would use it. You wouldn't use it there, but you would use it here. What is the square root of x squared? Well, you don't know if x is positive or negative. So let me remind you of something really important here. So here is a quiz. I'm going to give you a question, and you answer it in your mouth. Quiz question. And I've asked this for you before. And this is a common mistake, and it's an understandable mistake by the language of mathematics. Is minus x positive? Suppose x is not equal to 0. Is minus x positive or negative? Well, I'm going to guess a lot of you are choosing answer B, but that's not correct. The real answer is we don't know. without knowing the value of x. So let's let x equal minus 5. Then minus x, so x is negative. Minus 5 is negative. Then minus x is minus 5, which is positive. On the other hand, if x is equal to 5, then x is positive, and minus x is equal to minus 5, which is negative. So without knowing the value of x, we don't know if it's positive or negative, and that's the reason the square root of x squared, it has to be a positive value, right? But without knowing what x is, I do know that the absolute value of x is positive, so I'm good to go. It's kind of a picky point, but it is important later on, especially when you start headed down the calculus road. So that said, let's go on. And believe it or not, as much as the book makes a deal out of this rule, in later chapters they tend to forget it. So, A. This is 4A. We want to find the square root of minus 3 squared. Well, minus 3 is my x there, and I know it's the absolute value of minus 3, which is equal to 3. Let's do 4b. Let's find the square root. Oh, we just did that one. The square root of x squared is the absolute value of x. That it may be something that my math lab yells at you about. The fourth root of x minus 2 to the fourth. And what I need to be pointing out to you guys in each one of these situations, notice with the square root, the index is understood to be 2. So the power and the index are the same. So the power, so the number under the radical, or the expression under the radical, is raised to the same power as the index. So here, this is the expression under the radical. It's raised to the same power as the index. So I just use my rule. I don't have to do anything other than simply say it's the absolute value of x minus 2. Why the absolute value? Because the index is even. Now let's do 4d, and we're going to do the fifth root of 2x minus 5 raised to the fifth. Again, notice the index value and the exponent on the radicand are the same, but since the index is odd, I don't have to take the absolute value. It's just simply 2x minus 5. Let me go up and let's I'm going to grab GeoGebra really fast. We'll use it in just a bit, not right now, but it'll be coming. Okay, because the one thing I can't really do with this setup is graph. Show graph paper is really what I mean to say. So here we're having functions. Notice here, f of x would not be a function if we weren't always taking the positive root of x minus 4. So the first thing we're going to do is we're going to find the domain of these functions. So, and then we're going to, I'm going to go ahead and find the domain of both of these functions. but then we're just going to evaluate them at a given value. And the values that we're given is already in their domain. So my first function is f of x is equal to the square root of x minus 4. So since the radicand here, the index is 2, then the radicand, x minus 4, or the number under the radical, must be greater than or equal to 0. Because square roots of negative numbers aren't real numbers, and these are real valued functions. So I just solve for this inequality. So that gives me x has to be greater than or equal to 4. So the domain of this function is all values greater than or equal to 4. And over here with g of x, that's equal to the cube root of x plus 2. But since it's the cube root, the expression or the number under the radical can be positive or negative. So the domain of the function g of x is literally all real numbers. And we'll see this when we actually go to plot. So we're asked to find f of 8. 8 is greater than 4, so it's in the domain. So that's the square root of 8 minus 4, which is equal to the square root of 2. And for our class, you would just leave it like that. That's as far, sorry. I'm talking and not thinking. That's the square root of 4. 8 minus 4 is 4. And that is equal to 2. Now, for f of 6, then that's equal to, I just replace x with 6. So that becomes the square root of 2. And that's approximately, if you get out your calculator, 1.414, and that's all I have it memorized to. But if we were back in the classroom, this is the preferred answer, because that's exact. The problem with this exact answer is it doesn't help us locate it on the number line. So just read when you're doing my math lab homework, read what it asks you for. If it wants an exact answer, you have to put this. If it wants an approximate answer, the only thing you need to do is, well, you'll have to grab your calculator. You just need to know to how many decimal places, to how many places after the decimal they want it. So at any rate, over here, let's go back and do C. So we want to find g of minus 1. Well, that's the same thing as the cube root of, I replace x with minus 1 plus 2. So that's the cube root of 1. And we already learned that that's equal to 1, because 1 times 1 times 1 is equal to 1. And g of 1, g of 1 is equal to the cube root of 1 plus 2, and that's the exact answer. It's the cubed root of 3. And that's about, according to my notes, if you were asked to approximate it with decimals, that's about 1.442. So since a calculator could be involved in your My Math Lab homework, let's bring up a calculator, and so you'll know how to use that. So I'm using Linux, so I don't have the same programs that you all do, but I do have this calculator. And what I want to do is find the nth root of x. So I'm literally looking for a key that would say something like that. And I do believe that there is no such key here. Now, of course, I don't have to do it. I'm actually going to do it this way. No, I can't do it. I'll just confuse you. I can literally use x to the y and raise 3 to the 1/3, and that's the same. But that's something that we're getting ready to learn, so we'll just say you figure it out on your own if you're asked. You can do it. I know you can do that. Where else are we at? Oh, yeah. So we're going to plot, I think, graphing the nth root functions. So to graph an nth root function, first find the domain, and then find some points on the graph. If the index is even, then the radicand must be greater than or equal to 0. So set the radicand greater than or equal to 0 and solve the resulting inequality to find the domain, and then choose select items taken from the domain. So here we're going to do that. I give you a hint here, but let's just do it. Let's see if we can figure it out without me doing too much. Okay, so this is number 6 question. So we want to graph f of x is equal to the square root of x plus 1. So I already know this is a function. If I didn't know it was a function, I couldn't be using function notation. So I know it's going to pass the vertical line test. So the domain, well, the index is even. We don't write the index, but it's understood to be 2. So the index is even. So we need x plus 1 greater than or equal to 0, which means x is greater than or equal to minus 1. So the domain is all real numbers, including minus 1, that are greater than minus 1. So that is our domain. So I'm going to do this by a table of values. X and f of x. Remember, f of x is equal to y, such that is the square root of x plus 1. And every number I choose must come from this domain. So let's choose minus 1. Well, the square root of minus 1 plus 1 is the square root of 0, so I get 0. So now the question is, I kind of want to be able to graph this without using a calculator. So I want to whatever is under the radical, x plus 1, to be a perfect square. So the next perfect square is 0. So x is equal to minus 1. I've got that. So the next perfect square is, I want x plus 1 to be equal to 1, because the square root of 1, a perfect square is a number, a whole number, that is the product, for example, like 25 is the product of 5 times 5. So when I take its square root, I get a whole number and no fractional part. So the square root of 1 is 1. So I'm going to solve for x, and this gives me x is equal to 0. So if I put 0 there, then the square root of 0 plus 1 is the square root of 1, which is 1. Well, I'm going to continue down that pattern. I want x plus 1 to be perfect squares. The next perfect square is, after 1, is 4. So that gives me x is equal to 3. So let me do x is equal to 3. Then 3 plus 1 is 4, and the square root of 4 is 2. Now my next perfect square is 9. 3 squared times 9. So that gives me x is equal to 9 minus 1, which is 8. So I'm going to plug in 8. And the square root of 8 plus 1 is the square root of 9. It's going to give me 3. Let's do one more, or maybe 2 more. My next perfect square is 4 squared, which is 16. So that gives me x is equal to 16 minus 1, which is 15. And the square root of 16, 1 plus 15 is 16, and its square root is 4. And we'll do one last one. X plus 1 is equal to 25. So we have x is equal to 24. And 24 plus 1 is 25, and its square root is 5. So let's actually plot all of these numbers and kind of see what they look like. So I'm going to go ahead and enter in the numbers. So minus 1, comma 0. Right, there's that point. My next point is 0, comma 1. There's that point. My next point is 3, comma 2. There's that point. My next point is 8, comma 3. There's that point. Let me scroll out some. My next point is 15, comma 4. Not 15, comma 4. And there that point is. One more. And we found one more, and that was 24, comma 5. And there are all of my points right there. A, B, C, D, E, and F. So now let's actually plot the square root of x plus 1. And you see that our line goes right through all of our points A, B, C, D, E, and F. So that's more or less, let's zoom out, that's more or less what the square root function looks like. Notice we're only taking the positive values, so it passes the vertical line test. If we wanted to plot the negative square root of it, so this is another function altogether, it would be this red line down here. And it would also be a function too, because its plot would just be the red line. So I could not plot plus or minus all of the square roots, because then that would not be a function. So a function has to take this upper branch right here, it's called the positive branch of the square root, and this lower branch down here, it's called the negative branch of the square root. So I'm going to go ahead and erase these while I'm here, because we're going to be doing the same thing, except we're going to be plotting a cube function, and that's never easy. When you cube things, things get really big fast. So we're going to plot the cube root of x. So what we want to do is we want to choose values which are perfect cubes. Again, we're going to make a table of values. So our function, is it f of x? Are we still using f of x? Yep, we're still using f of x. I forget which number this one is. It doesn't matter. You all have it there in front of you. F of x is equal to the cube root of x. So what is our domain? Well, since the index is odd, x can be any real number. So the domain is minus infinity to infinity. So that's going to help me plot it. So let's choose some easy values that are perfect cubes. X and f of x is equal to the cube root of x. So let's choose 0. And 0 times 0 times 0 is equal to 0. So it goes through the origin. Let's choose 1. Well, 1 times 1 times 1 is equal to 1. Let's choose minus 1. So that's the trick, is once I find a positive number, then I can choose, and I find its cube root, then I can choose a negative number and find its cubed root as well. So the next one is 2 times 2 times 2, which is 8. So if x is equal to 8, its cube root is equal to 2. If x is equal to minus 8, its cube root is equal to minus 2. Let's do one more. 3 times 3 times 3 is 27, and 3, and minus 27, and minus 3. So there's several values. Let me sketch them down right here. So the origin, 1, 1, minus 1, minus 1, 8, and 2, minus 8, minus 2, 27, and 3, minus 27, and 3. So let's actually plot those. Let's go over to GeoGebra, and let's plot the origin, 0, 0. Got it. Now let's plot 1, 1. Let's plot minus 1, minus 1. Now let's plot 8, 2. And now let's plot minus 8, minus 2. Now let's plot, we jumped up to 27, 27, 3, and minus 27, minus 3. We can do one more, can't we? We can do 64, 4, and minus 64, minus 4. So let me zoom out. So there we have it. So let's actually see what it really looks like. Input. So I'm going to have to do this a weird way. Sorry, x raised to 1/3. Please check your input. So x raised to the okay, that does it. So there we can see, zooming in closer, we can see, where's my pan button, that this is literally, it's kind of like, this section over here is kind of like the square root of x, but it increases a little bit faster. And then if you were to flip it over the x-axis and then flip it over the y-axis, you get this section. But notice it is, the domain is all real numbers. When we did the square root, we didn't have any negative numbers as our input values, and here we do. Okay, now what do we have to do? Graph and graph. Seriously, is that it? I'm showing that that is it, so we have finished 7.1. This week we're supposed to do several, so I'll try to get as many videos uploaded as I can.